Welcome everybody to another OTTER talk. Today we have invited Ben Russo from Farmingdale State College in the SUNY system to give us a talk on learning with kernels. And he's accompanied his lead slide with a beautiful rendition of an OTTER to start us off. So thank you, Ben, for being here, and take it away.
Yeah. So I showed this to my wife, and she's like, I don't know what that is. So hopefully that looks like an OTTER. Anyways, thanks for coming to my talk, and thanks for giving me the opportunity to talk. With kind of machine learning, I basically know enough to be dangerous, so I'm going to do my best here. And I'm going to talk about a few topics that are what I think are accessible to people who have a kind of functional analysis or function theory background, and maybe some operator theory background as well. So we're not, I'm not going to try and get into like the very detailed specifics about how these things are done, but just kind of give you an idea of like kind of the function theory and probability theory that kind of goes along in the background, and just kind of show some implementation and some neat things that they do. So kind of the classic starting place in a lot of these things is the binary classification problem. The goal of binary classification is to kind of make new predictions based on some previously observed data, right? So for instance, we could have some data points, maybe, these, for instance, lie inside R2, right? And so we're going to call our previously observed data our training data, right? So to kind of formalize this, we're going to assume that this data lies in X cross Y. So X is usually going to be some sort of subset of RG or RN, whatever letter you choose. And Y is usually going to be a subset of R, and it's going to be kind of your target variables that you're trying to model. All right. So here, this point, this is a point in R2, and it's going to be colored according to its Y. So for instance, the Y value for this point is going to be -1, and the Y value for this point is going to be +1. All right. Let's just kind of think about this. So for instance, our vector X could be a vector of, let's say, clinically measured value. So let's say you have a patient, and you measure their height, weight, age, cholesterol, and things like that. And then Y could be an indicator of whether that person in that data set had, let's say, a particular disease. Totally not relevant to our lives at this point right now. And so now the goal is that if you have some training data, right, and you introduce a new point that you don't quite know what it is, you want to be able to classify this as either red or blue when you introduce that new point. All right. Let's see. So essentially what we want to do is we want to learn a function f of x. So this is a function from x into the target variables y. That's a good approximation to a possible response to an arbitrary input x. Right. So we're going to make some assumptions on our data. So we're going to assume that past and future pairs x and y are generated by some sort of unknown probability distribution p on x cross y. And so that's the kind of important part, is that we won't know what this probability distribution is. Right. We're also going to assume that the input values x are generated according to some sort of marginal distribution. If we don't know what this is yet, we'll just wait a couple of seconds. And then we're also going to assume that our responses y are generated according to some sort of conditional probability. So the probability that y is true, given some sort its input x, right? And so the probabilities kind of relate to each other like this. All right. So So what do we, so it's really kind of the first question we have to ask is, what do we mean by learning, right? And what does it mean to improve, what you learned here? And so the way that they, one way to kind of encapsulate this is through this linear functional here, right? So it's just an integral over x cross y of this measure that we had here, okay? Of this thing that we're going to call a loss function, right? So essentially, if you make a good prediction, the loss function is going to maintain. If you make a bad prediction, the loss function is going to go up, right? So for instance, in our binary classification problem, as we're trying to train our method, we're going to try and minimize this integral, right? So the kind of expected loss of f is what we're going to be calling the risk of f, right? And so essentially, our goal is going to be to minimize this functional over some set of functions, typically all the functions that we could possibly input, right? And actually find what this f is, right? So it might be tempting just to kind of just use your data and assign some sort of loss function like classification loss, which again, just assigns a point if you misclassified something, and just kind of take the average loss of your data and try to find a function that like minimizes that loss, and that will converge according to the law of large numbers to something like that, but that's actually not enough, and essentially you could run into what's called overfitting issues. So this decision function essentially might just memorize the data, your finite set of data in some sense. And so you typically need to evaluate your loss function over kind of larger and larger sets of functions to kind of avoid these things, right? And also I do want to point out that again, we don't typically know any information about P. And so this information has to come from the data itself. All right, it's not like somebody is going to sit there and write down a formula for P for you, because we just simply wouldn't know. Right? You can write down what the loss function is, and so our goal is to really try and figure out the minimizer for this thing. And so we're going to talk about this method called support vector machines. And support vector machines, which are abbreviated as SVM, and I'm just going to say SVM because there's just always a bunch of acronyms or initialisms, whichever they are. So SVMs can be shown to find the function with a near optimal response without actually having to know anything about P specifically, but just using the data. Right. So kind of the downside of this is what we call the no free lunch theorem, which says that, okay, the SVM procedure will produce an F that should get near the optimal response, but in general, we have no idea how quickly that'll happen, right? Or how much data will be needed and things like that. But you can show under mild conditions that it doesn't go terribly for certain things. All right. So the support vector machines, SVMs, are a solution to this binary classification problem with geometric origins. And so I kind of drew this picture in a way that you would say, well, what is the dumbest thing I could do? The dumbest thing I could do is to just kind of draw a line between the red points and the blue points and say, okay, if you're on one side, you're a red point, and if you're on the other side, you're a blue point. Simple enough, right? And then the decision function, which classifies future points, will just be this sign function here, right? So if you're on one side, you're red. If you're on the other side, you're blue. And so you say to yourself, okay, well then this new point that I've introduced, it's going to go be friends with the blue points because it's on this side of the decision boundary. All right, that's great, and that's pretty simple enough. And to show that you can have the separating hyperplane, it's just some linear algebra. But you say to yourself, well, there really should just be a bunch of lines that cuts these two data sets in half, right? And so there's going to be an infinite number of separating hyperplanes. And so what we do is to assure that we have a uniqueness condition for the separating hyperplane, we require what's called the maximum margin condition, right? So we're going to seek a solution that kind of puts the most space on either side of our hyperplane to the nearest point in our training data, right? So I do want to step aside for a second and say that when this is actually done in real life applications, you don't just have training data and then new points. You do what's called a test train split. So you have some sort of given data that's already classified, and that all of it could be classified as training data. And then you take that data set, you take some of it and say, I'm going to train on this, and then I'm going to kind of confirm what I had on this other set of data that I already know is correctly classified. But we're not going to get into that here, other than just that brief explanation. Right, and so we can require this kind of uniqueness by just saying we want this maximum margin condition. In general, that's also not what's really done. We use some sort of soft margin instead, and we'll talk about why in a little bit. Okay, so that solves this hyperplane that we have. And that's going to be unique, that's fine. But again, I drew a very kind of convincing picture here that this should work. And so does this always work? And the answer is, well, no, obviously. A linear decision function may not work. So I drew these things called moons, right? So they're kind of interconnected here. And there's not really a line that I could draw through this data where I can well, separate them and have them correctly still on the correct sides, right? What I really want to do is I want to kind of snake in between this data and write my decision function that way, all right? And so the way that this is solved is by using some function space theory, right? So we're going to use what's called a feature map. So a feature map is going to be a map from your set that your data lies in. Okay, this is that's the x and this x cross y. And we're going to try and find a map that has this kind of inner product condition here, right? Where here, this k, let's just cut to the chase. This k is a reproducing kernel, right? And so what kind of happens on this kind of high level is we take our data that's over here in X and it's nonlinear, and we use this feature map to send it over into a Hilbert space. And so the downside is, well, now it's a Hilbert space, and that's not really a downside for anybody who does operator theory. But the upside is that now, in theory, this data now becomes linearly separable in some sort of weird condition. So we just have to now solve the same kind of minimization problem that we had over here, but now just do it over a Hilbert space. And so your immediate question should be, what is this feature map thing? And the kind of upshot is that we don't actually care what it is. This is really just kind of a theoretical crutch in some sense, right? So when we actually think about the SVM procedure, everything is entirely calculated in terms of these inner products, right? So this minimization problem, the solution to it is calculated in terms of these inner products, which are given by just kind of the evaluation of the kernel at those points X and Y, right? And so we don't actually have to worry about what that kernel or what that feature map is. And in fact, most papers don't ever talk about it in general. And so we're just gonna move right along, okay? All right, so I keep saying the word kernel. And so these kernels come from what's called reproducing kernel Hilbert spaces. So I don't know what everybody's kind of familiarity is with these kinds of spaces, so I'm just gonna talk about what they are. So again, we have again our data lying in some sort of set X, right? And so a reproducing kernel Hilbert space over a set X is going to be a Hilbert space of functions such that point evaluation is a continuous linear functional for all X and X. So what does that mean? Well, it's called a reproducing kernel Hilbert space. And so Riesz representation guarantees that for all X and X, there's a functional K sub X, which we're going to call the kernel at X, that the point evaluation is going to be given by inner producting against the kernel function at X. Right, and so there's some notation here. And so kind of the nice thing is, let's go back up a little bit. We kind of have freedom of choice of what kernel function we're using. Typically, since this is supposed to be some sort of inner product, this just has to be a positive definite function and symmetric, because again, this is going to be a real inner product. And so we have a lot of freedom in this choice of kernel, right? And so what this theorem says is that if K is a symmetric positive definite kernel on a set X, then there's actually a unique Hilbert space that has it as its reproducing kernel. And so what this means for us is that we actually have freedom in what reproducing kernel Hilbert space we want to use in this SVM procedure that's kind of mysteriously out there. Now, when I say freedom, I mean, you know, if you want to code this up yourself, you're allowed to choose whatever kernel you'd like. And there are options for that in Python. But in general, there's a couple of spaces that are kind of usually used. But let's give an example of a reproducing kernel Hilbert space. So for instance, the Hardy space, everybody's favorite space, is the set of analytic functions having power series representations with square summable complex coefficients. This is these things here. You can define the inner product on it just by this, and its norm, like this. All right, so that's great, and it's not very difficult to prove that this is a reproducing kernel Hilbert space. You just have to prove that point evaluation is a continuous functional. So slap on Cauchy-Schwarz and call it a day. All right. And the great thing is that, you know, you can just kind of use some geometric series arguments to show that the reproducing kernel for this space should be the Zago kernel. All right. And so here's an example of a reproducing kernel Hilbert space, and its kernel. So its kernel at W is going to be given by 1 over 1 minus W bar Z. Now, so this is the space that, you know, everybody here loves, but this isn't the space that's typically used in a support vector machine. What's more often used is the space of Gaussians, right? And so when you're coming from machine learning land, you don't actually care about what this function space is because you're only usually working with the kernels, which are dense in the space, by the way. But I've only actually ever seen one book that actually writes down what the space is, and it's this space, right? So this is the space for the complex Gaussians. And again, since we're talking about the real world and trying to use this in a real sense, we have to take a real version of that. And so you can define the real version of this Gaussian space by taking just the the real part of these functions that live in the complex space. All right. And so if you're really paying attention, you might notice that I have some sort of dependence on this gamma here, which is not a mistake. So this gamma is going to be this kind of adjustable parameter, which is sometimes called kernel width. And it's going to be one of the things that you adjust when you actually try to do something when you're SVM. All right. All right, so SVMs, these procedures, these use these reproducing kernel Hilbert spaces in the background. So let's talk about how they actually solve this. All right. So to kind of turn this into a convex optimization problem, what's done is that you'll replace the classification loss, which is this kind of step function thing, with a kind of convex version of this, and this is called the hinge loss. Right. And so we could take what's called the imperial risk for your data set. Again, this is your data set down here. Right. And then essentially solve our minimization problem over this space. And so we have this thing called the representer theorem. So if we have a convex loss function, and D is our data set, we're going to let H be just a reproducing kernel Hilbert space over our X. So for all lambda, there's going to exist a unique solution to this kind of minimization problem, in which case our SVM minimization problem can be put in this form. And kind of the nice part is that additionally, this solution has to be made up of the kernel functions at your kind of data points, right? So it has to be a linear combination of your kernel functions centered at those data points. So in other words, the Gaussian centered at your data points, right? And so again, we have to kind of justify that this solution gets close to the overall minimal risk. And so if we define kind of, let's say, the risk over just this, our Hilbert space, it can be shown under kind of nice enough condition. This is actually the minimal Bayes risk, is what they call it. All right. So the risk over the Hilbert space is going to be equal to the actual minimal risk that you have. All right. And so now we just need to kind of have some sort of information about how this thing gets close. And those
Sorry,
are,
Ben.
yes.
Oh,
yes.
go ahead.
Just that this optimization problem exactly the sorry. Yeah, sorry. So is this class optimization problem the exact problem you proposed before? Like this is a soft version?
Yeah. So yeah, you take the version that I had before, throw in some slack variables to get kind of a soft margin version, and then do some manipulations, and you can kind of put it in this form. So I didn't want to, run through a lot of the details of that, but yeah, essentially this is the version we had from beforehand, using this kind of imperial risk thing here. I hope that's answering your question.
Yeah, thank you.
Okay. Anyways, so we have what's called these oracle inequalities, which kind of show how this kind of the solution to this kind of imperial risk problem gets close to actually the minimizer over the Hilbert space itself. Right. So this A substitute lambda, this is something that goes to 0 when lambda goes to 0. And so it's going to be this kind of fine balance between kind of how many data points you have and what this lambda is here. Now, so you should ask what this lambda thing is. Yes.
A quick question, rather it's a question from the chat. So the question was asked about the soft SVM, which you answered earlier. But I guess I also have a similar question to Arthur. What is soft SVM?
Oh, so the soft SVM, instead of having like a hard margin in which essentially none of your data points are misclassified, the soft margin SVM kind of allows for at least a couple of them to be misclassified, right? They can get past that wall a little bit in some sense. I don't know if I have a better answer for that right off the top of my head right now, though.
So didn't you set up the problem like that almost near the very beginning, where you were like, just what if your classification problem looks like it's all over the place? Then you apply this, I forgot what you called it, but this function that transforms it in such a way so that you can linearly.
The feature map, yeah.
Right.
Yeah, so, hey, Arthur. So I'm not sure if I'm understanding your question right now, but I can think about it. And is it okay if I answer it after the talk?
Yeah, for sure.
Yeah.
Thanks.
All right. Because yeah, nerves. Anyways, so I guess let's just keep talking about what this lambda is. So this lambda is this kind of regularization term. And so essentially it's going to punish kind of overly complicated functions, right? So overly complicated functions in our Hilbert space are thought to typically have kind of like larger norms, right? And so this lambda here is supposed to kind of punish that, so we don't overfit the data. When we do an example of this, I'll show how you can get overfitting by changing this lambda parameter, right? And essentially, we don't actually solve this problem. We solve the Lagrangian dual of this problem and use some sort of convex quadratic techniques to solve those problems. And so that could be things like interior point methods. All right. So let's actually look at some things just to kind of see what happens. All right, so here's a nice linear example, and I don't know if everybody can see this easily. So I'm just going to set up some sort of fake data here. So this is what's called the make blobs function. It's going to produce two different blobs, and I did this because I want it to be linearly separable. And this is just some sort of rescaling thing. And so here I'm setting my preferred kernel just to be dot products, right? So we're not going to use any kind of feature map. This is just going to be the linear version of this, right? And this is the function to kind of do what we want it to do. The rest of this is really just kind of plotting this decision boundary here. But the actual like code to generate the solution is entirely contained in these lines. And this is one of the reasons I wanted to use Python. All right. And so I've circled a couple of these points. So these points are the support vectors. So when you find the solution to these things, it turns out that only a few vectors will actually contribute to this decision here, right? And so this is this decision boundary is literally just kind of a level curve for our decision function in some sense. So here I think this is +1, and this will be like -1 over here. All right. So we can look at essentially a nonlinear example, right? And so here is my nonlinear version. And so this is going to be, I think, hopefully using the Gaussians. And this gamma here is kind of one of these parameters that you can kind of adjust and get some things out of. All right. So let's run this. And so here is my non-linearly separable data. And kind of using the same procedure, I can generate this decision boundary. Again, we're just kind of solving this problem using inner products. Now, if I adjust this gamma, I think this one will make it worse. Yeah, here's an example of overfitting. So if I adjust that gamma, which you'll have to read the documentation, it's either the same thing as my gamma or maybe 1 over that version of gamma. Anyways, if I increase this and this, I'll get some extreme overfitting. And so it's just going to completely encircle your data here. And all of these are now support vectors, as opposed to over here where only a few of them were. Okay, so that's kind of SVMs in a nutshell, or support vector machines in a nutshell. Okay, all right. So,
hey Ben.
Yes.
So Arthur asked a follow-up question there. He asks, is there a feature map associated to this? And does the code figure that part out?
So there is, in theory, a feature map associated to this, but again, it's the feature map is not really the thing you should be focusing on. It's just kind of there as like this device to kind of help people think about this. Again, everything is really kind of done in terms of the inner products. You never actually write down this map, and you never actually use it in a capacity other than inside the inner products, in which case you're using the kernel, right? We'll see a more extreme version of this in the methods that we're going to be talking about next, okay? To try and give you an idea of like really how these things are used. All right. And this is kind of the essence of the kernel trick in some sense. All right. So that was what's called a supervised method, because you have some sort of target variables you're trying to model. We want to talk about some sort of unsupervised things as well, in which case you're just saying, I have data, tell me something about it. All right. So another thing that's kind of, I think, would be natural for operator theorists and just really anybody with a good grip on matrix theory to do is learn how singular value decomposition is used in kind of data analysis. Right. So SVDs exist, right? But kind of the neat part about this is that if you want a lower rank approximation to your matrix, the rank R SVD truncation, so just taking, let's say, the first R columns, is the optimal approximation under the Frobenius norm, right? And so essentially the idea is that a lot of the information about whatever your matrix is kind of captured and organized in a way that really the first few columns kind of capture most of your information. So we can see that here. Let's see. All right. So here's this kind of SVD procedure that I have going on. I'm going to start running it. It's going to take a photo. It's going to take the grayscale version of that. So a photo is really just a matrix of values that indicate the brightness of each pixel, right? And so I'm going to take the SVD of our image, and I've set some sort of threshold here of 10. And so I'm going to take the columns that correspond to the singular values over 10. And so that's actually a good lot of them, right? So this is my cat Butter. She's adorable. And here is a recovered image using the SVD decomposition. So I only used 151 of the original columns, and I think there was only like 3,000 of them, right? So I only used 151 of these because I took a large amount of the singular values. So I can also take less of them. So that I only grab, let's say, like the first 10 or so now. And if I run this again, my reconstructed image is not going to be as good as this, which took more of the columns of the SVD. Sorry, this one takes a little bit of time to run. So here we are. There it goes. Maybe, maybe, maybe. Come on, come on, come on. This is why code demonstrations are always just forever. There we go. Okay, so here I took less columns of my SVD decomposition, which I guess is kind of redundant. And so you can still see that it's kind of Butter, but it's not really her. But you can get an idea of all of this. So really a few columns of your SVD will kind of encapsulate a lot of the information of your matrix. And so we call this kind of feature extraction. All right. So let's get out of here. Kind of related to this is principal component analysis. This is another form of dimension reduction. And so the idea of principal component analysis is that if you're given a set of centered observations, so just zero mean observations, the PCA procedure diagonalizes the covariance matrix, which encapsulates, how the data varies in some sense. And so the first principal component, the largest kind of the vector corresponding to the largest eigenvalue, that's what maximizes this. And essentially, we're finding the directions in which the data varies the most. And so if that's only a few directions, we can kind of take just those directions and get most of our information out of them. All right. And kind of on the side, we'll just say that a lot of times SVD is used to actually compute the principal components as well. So there's another thing here. So we're going to do something kind of haunting, and we're going to do what's called the eigenfaces example of this. So the eigenfaces example, we have kind of a database of faces, and we're going to run PCA on the photo data, right? So here are the lines that I need to do this decomposition. I'm going to look and take 150 principal components. All right, and so let's just do that. All right, so these are kind of essentially the first few faces in the data set. And well, there's that. But the interesting thing is that you can now take that data set and compile what's the average face. And so this is the average of all the faces in the data set, which I guess we are kind of blobs in some sense. But what's really haunting are the principal components themselves. These are the eigenfaces for our data set. Right, so essentially we're trying to cover a wide part of how this data varies. And so you kind of get these weird pictures here, but these are what's called eigenfaces. And so this technique has been used in face recognition software. All right, so that was weird, but let's bring it back to kernels. And so there's a kernelized version of this. So instead of looking at the covariance matrix, we look at this covariance operator, which is this finite rank operator. And we're using this kind of, I'm using the operator theory notation here. That's not how this is written in the original paper. This is positive semi-definite. That's a pretty easy thing to see just by doing basic calculation. And so we can run the same idea, but now we're just over a Hilbert space. And so our vector is going to be a linear combination of these things. And again, this is this says this phi here. This is the feature map for this point. But when you actually work with these things and you actually write down the equations, notice that every one of these equations is really just in terms of the inner product. So you never use this feature map in general. You're really only looking at inner products of these feature maps, and this is going to be given by the kernel itself. So this is kind of when we say the kernel trick, this is what we mean more or less. Is that these inner products are not actually inner products that are, I mean, they're inner products in the Hilbert space, but they're really just evaluation of the kernel function itself. Right? And so that dramatically kind of speeds up computation in some sense. Oh, I wrote that here. So you can do that, and you can do these things and write down kind of a matrix equation for this. And this is called the Gramian for your kernel. And again, you can use whatever reproducing kernel Hilbert space you'd like, total freedom there. But again, they usually use the Gaussian one. And you can solve for your coefficients alpha that show up in your eigenvectors by solving this just matrix equation here. All right, so lambda and m are constants, by the way. All right, and so I did say this bit about kind of needing centered data. This is also handleable in the Hilbert space setting. Essentially, just kind of subtract off the average of this. And again, we don't really do that. We do everything in terms of this kernel here, right? So everything in terms of the kernel. And so we just kind of take our Gram matrix and adjust for it with these matrices, J sub m. All right. And so now you can just run the PCA procedure on this new matrix K tilde here. All right. So why do we need kernel PCA? Well, PCA again tries to find these low dimensional linear subspaces that explain most of the data. But sometimes your data might not be confined to a linear subspace in some sense. You might get like, so here we have some data lying on this on these circles, right? And so kernel PCA is used to kind of work with these kinds of things, right? We could see this here. So one last thing. So we're going to run PCA and kernel PCA on that kind of, on circular data like we saw before. And so these points are going to be colored basically just so you can keep track of them. Okay. And so let's run this. And we'll see here, this is the original space and the original data. And this is what happens when you apply just regular PCA. Basically, nothing happens to it. And we don't get really any new information out of this. But when we run it with kernel PCA, we now can separate these data, or this data. And so again, you can think of this as like some sort of transformation procedure on your data, in which case, now that it's in this form, we could run a linear SVM on this as well to kind of do some classification. All right. So, like I said before, PCA and kernel PCA have been used in face recognition. Here are the titles of the papers if you're curious about them. And so we could do that. And this is going to be the last thing because I don't want to run over. But I want to talk about the scheme of novelty detection using kernel PCA. All right, and again, the principal component should capture most of the data. And so we're going to see how we can use that to kind of detect weird things that are going to happen. All right, so we can define this kind of potential for a point, a data point Z. Again, in terms of this inner product, using this centering idea. And again, this is always written in terms of the kernel itself. And so if VK is, let's say, the kth eigenvector in your PCA analysis, we can project this phi tilde of Z onto its kth eigenvector for the covariance matrix. And we're going to define the recreation error for a point as just kind of taking this and subtracting off the projection, more or less. And so we're essentially trying to see how well your new data point is constructed by your vectors. And so you can run through this thing and actually, again, calculate these things in terms of the kernel. And so the general scheme is that if you have some training data, you're going to compute the max recreation error using a fixed set of nonlinear principal components for your training data. And then when you start to introduce new points, they're going to be good if they're under this threshold that you're setting using the recreation error, and they're going to be bad if they're over this threshold for our recreation error. Okay, and so this is the last thing, and this is the only thing I'm going to use MATLAB for. I'm using it because the person who wrote this paper was kind enough to put their code on their website, so you can actually find it on their website. Oh, I have it down here. And so this is their function to kind of compute the recreation error for some data set you're going to give it. And here's the kernel and the function to compute the recreation error. And essentially, we're just going to load up this data. I'm going to say run this scheme on this A using a kernel width of 0.4 for that gamma. We're going to take 40 principal components, and we're going to say that none of them are outliers for this data set, or none of them should be outliers. So let's run that. And here it is. So this is a plot of the recreation error for our data points. Oh, and our data points are just every point inside this square. And so these red contours, these are actually just the contours of our function here. And so inside the contour, these are our normal data points. And then if we lie outside of the contour, these are going to be our weird new data points that maybe shouldn't be a part of our data. So this is, again, an anomaly detection scheme. Right? I could say that some of them should be a little bit weird. So let's say we took 100. And so what this is going to do is it's going to take that training data and say, okay, 100 of these points should be weird. And it's going to tighten our contour. And again, let's see, is it here? Yeah. And so now if we look really, really carefully, we'll see that some of our points are now outside of our boundary. And so these are going to be the weird points according to this idea. All right. So what do we do now? Well, that was the demo. So let's talk about some current work if you are interested in these kinds of things. So again, I don't want to claim to be an expert of any sort. I have kind of my own side route through these things. But there's currently a lot of work going on in applying machine learning methods to dynamical systems. And kernel methods and data-driven modeling kind of have a pretty healthy research community. So I put a link here to a recently held online conference. And you can go watch a lot of talks about kernel methods. And again, these are kernels from reproducing kernel Hilbert spaces. Again, my background's only in functional analysis and operator theory. And so, some of the things that I've been involved with are system identification techniques. So given some sort of trajectory data for a dynamical system, can we identify governing equations? And so that's a paper that I've been involved with. And then here's some other things that happened as well. And there's also this thing, another form of system identification called dynamic mode decomposition. And essentially, you're running the SVD procedure, again, on dynamical systems data, right? But this dynamic mode decomposition involves what they call Koopman operators, but these are really just composition operators. So if you want to start looking at operators and kernel methods and kind of machine learning things, dynamic mode decomposition or kernel DMD might be a route that you want to get into. So that's really all I have to say. I hope it wasn't too rambly, and thanks for listening.